Welcome to this explainer. Today, we're going to unlock the hidden mathematical rhythms that literally govern the world around us. Have you ever noticed how much of our universe is just things repeating themselves? From the rhythmic swing of a grandfather clock to the hyperactive, invisible vibrations of atoms, there's a fundamental pulse to reality. We're going to break down exactly how this works, pulling directly from our source material on oscillation to show you how everyday objects follow these strict mathematical rules. And if you stick with me, we're going to apply these very same rules to a massive science fiction thought experiment, dropping a mass through a gravity tunnel straight through the center of the Earth.
Okay, let's dive into this. Here's our roadmap for today. First, the rhythm of motion, then springs and Hooke's law. After that, the math of oscillation, visualizing harmonic waves, and finally, pendulums and gravity tunnels.
All right, section 1, the rhythm of motion.
Think about a bouncing ball, or, a swing set at the park, or even the pulsing of a speaker cone. What do they have in common? Well, they all return to exactly where they started. In physics, we call this periodic motion. It's defined as any motion that repeats itself at strictly regular intervals. To really understand this, we need two key measurements. The first is the period, represented by a capital T. The period is simply the time it takes to complete one full cycle of the motion. The second is frequency. If the period is how long a cycle takes, the frequency is how many cycles happen in a single second. They're basically two sides of the same coin, giving us a perfect way to measure the pulse of any repeating system.
Moving on to section 2, springs and Hooke's law.
Take a look at this classic simple spring mass system. We've got a mass attached to a coiled spring, just resting perfectly still on a flat surface. That resting point, labeled O right there, is the equilibrium position. Right now, it's perfectly happy. There are no external forces messing with it. But what happens if we disturb that piece?
Let's really animate this process in our minds. Step 1, we pull the mass to the right. That distance we moved it, that's called displacement, or x. Step 2, the exact moment we stretch that spring, it wants to go back. It fights back with a restoring force. This brings us right to Hooke's law, which states that this restoring force is directly proportional to the negative displacement. Basically, the further you stretch it, the harder it pulls back in the opposite direction. Step 3, we let go. The spring yanks the mass back toward the center, but it's moving with so much momentum that it whips right past the equilibrium point, violently compressing the spring on the other side. And boom, we have our oscillation cycle.
Next up, section 3, the math of oscillation.
Now, to really understand this perfectly ordered dance, we have to look at the math. Don't worry, it's a beautifully simple story told in 3 parts. Part 1 is displacement, literally just where the object is at time t. Our formula is x equals a sine omega t plus delta. That a is the maximum stretch, or amplitude, and that sine function, it perfectly maps out the smooth, sweeping back and forth motion. It acts kind of like a high-speed tracking tool, pinpointing our mass millisecond by millisecond.
Part 2 is velocity, or v. Velocity is simply how fast that displacement is changing. Using a little calculus to find the rate of change of our first equation, we get v equals omega a cosine omega t plus delta. Notice how we shifted from a sine wave to a cosine wave? That means the speed isn't constant. It dynamically surges as the mass zips through the middle and then instantly brakes to a total halt at the extreme edges.
And part 3 is acceleration. How fast is the velocity itself changing? We take the rate of change one more time, and we arrive at the ultimate punchline of this math. A equals negative omega squared x. Acceleration equals a negative constant times displacement. Literally, this is the mathematical holy grail for this topic. It proves that the acceleration is directly tied back to how far the object is from the center, pulling in the absolute opposite direction. This specific relationship is the very definition of simple harmonic motion.
All right, section 4, visualizing harmonic waves.
Let's see this mapped out. Notice how these stacked, elegant waves, which are derived directly from our formulas, share the exact same rhythm, but they're staggered perfectly out of sync with one another. We've got displacement on top, velocity in the middle, and acceleration on the bottom. They never peak at the same time.
Now, what's absolutely fascinating is the contrast between these top 2 graphs. Look at the displacement curve. When it reaches its absolute peak, meaning the spring is stretched to its absolute limit, drop your eye straight down to the velocity curve. It crosses exactly at 0. It's a brilliant visual proof that for a split second, at the very edge of the abyss, the mass hangs completely frozen in time before accelerating back.
And as this mass slides back and forth, its energy is constantly transforming. The source material outlines how potential energy, stored up in the stretched spring, converts into kinetic energy as the mass gets moving. But here is the crucial takeaway. The total energy of the oscillator remains completely constant. It is always proportional to the square of its maximum stretch, or amplitude. The energy dynamically sloshes between potential and kinetic, totally locked in a closed, lossless harmonic engine.
And finally, Section 5, Pendulums and Gravity Tunnels.
Physics is universal, right? So let's scale things up. A classic simple pendulum is another perfect example of harmonic motion, but there's a catch. The math only acts as a perfect harmonic oscillator at very small amplitudes. At tiny swings, gravity acts exactly like our restoring spring. But what happens if we push gravity to the absolute limit?
Imagine this thought experiment derived straight from our source. You dig a tunnel straight through the center of the Earth, from one side all the way to the other. You stand at the edge and you drop a massive object straight down. What actually happens to it?
As an object plummets down this tunnel, something wild happens. The amount of Earth mass pulling on it dynamically changes. As it plunges deeper, the gravity pulling it inward acts exactly like the restoring force of our stretched spring. It pulls harder and harder the further away the object is from the center, always trying to yank it back to the middle.
And this brilliantly illustrates the exact same math we just learned. It perfectly mirrors our tabletop spring. Step 1, the body drops. Step 2, internal gravity acts as our proportional restoring force. Force is proportional to negative r, the distance from the center. Step 3, the object screams past the Earth's molten core at maximum velocity, slingshots up the other side of the tunnel, brakes perfectly to a halt at the surface, and plunges right back down. Falling through the Earth is literally nothing more than a giant, planet-sized spring oscillation.
And the absolute most mind-blowing part of this document, the source calculates the exact period for this planetary oscillation. If you dropped an object through the Earth, it would take exactly 84.2 minutes to complete one full round trip, down and back in just under an hour and a half, powered by absolutely nothing but the beautiful, predictable math of simple harmonic motion.
Which brings us to the end of our explainer today, but I want to leave you with a challenge derived right from the questions at the end of our source text. Take a look around your room right now. Can you spot the hidden linear, circular, or elliptical harmonic motions happening right in front of you? Because whether it's a slinky on a desk or a hypothetical gravity tunnel through a planet, the mathematical rhythms of the universe are everywhere, just waiting to be calculated. Keep exploring, and we'll see you in the next explainer.